quantum many-body problems, say. And pretty much, you know, the earlier discussions were the other direction, where I tried to use quantum many-body physics insights to design or improve some hardware for quantum information processing. Now, you all know quantum many-body problems, I guess, but just to be sure, what are we thinking of? Well, typically, you know, it starts as a Hamiltonian. Not always, but typically. And let's assume for simplicity that this acts on a Hilbert space. So H, you know, on a space of dimension equals 2, let me call that m, and let's assume it's a power of 2 to the m. Now, that's not always, but you can figure that's convenient if you use qubits to encode your Hilbert space. So let's do that. So today we'll see some small m's in the examples, but obviously the plan is to make m big and do hard problems. So yeah, typically what are you after? Well, the usual things. You like a spectrum, you know, eigenvalues of this Hamiltonian, the ground state in particular, but maybe also excited state energies. You like to have the states, the eigenstates. In particular, you like to have the ground state and things like that. If you have those, you can start doing correlation functions, correlators. And the other thing you would like to get your hands on, which is typically hard using regular methods, is dynamics, quantum dynamics. So let's say the operator e to the I times h times t. So dynamics, quantum dynamics. So for all these things, there is a story of how you can employ a quantum computer situation. Okay, so clearly, I guess this is a physics school, so you probably have in mind one of your favorite quantum many-body physics problems, but a lot of this methodology is applied in chemistry, quantum chemistry. So there's this QC squared, you know, I'm in regular group meetings that are called QC squared, which is the quantum chemistry for, you know, the quantum computing for quantum chemistry business, so to say. So tomorrow I'll do one, you know, mini example of that, just to show you how that goes. But it's a big field, and some of the hope is that maybe this particular field right here could be the place where, let's say, quantum computers strike first, because there can be problems that require not too many qubits, and that could maybe even be done on this noisy intermediate scale hardware that we are having these days, and that could still make a difference as compared to other available methods. But you know, this is all to be seen in the future. Okay, so if this is your general wish, you know, you try to get your hands on these kind of features for Hamiltonian. So how can you approach this thing? Now there's sort of a clear message. There's two strategies that you can deploy on quantum hardware. They're very different. I guess they're equally interesting, but they're different. So they go with acronyms as always. So two approaches. One is called QPE. Well, the Q is quantum that you figured. This stands for quantum phase estimation. Let me write that, quantum phase estimation. So it's if you wish, a trick to measure phases of unitary operators. So quantum phase estimation. If you're lucky, it's actually exact, so it's not estimation, it's actually determination. But then, you know, you need a bit of special circumstances for that. And the second approach is called VQE. The Q is quantum, the V is variational. So this is what goes as variational quantum, and then the E is eigensolver. So it's like a machine, a program, a software package that cranks out eigenvalues, eigenstates of complicated many-body Hamiltonians. So these are the things that are available, and roughly speaking, my plan is to focus today mostly on QPE and reserve tomorrow for the VQE approach, and that way rounding off my story. Now, I thought before getting into details, let me try to be a bit more specific on what these methods need as input and what they give you as output, right? Well, obviously the input is this Hamiltonian, output is my list of features, but there's some more details to this that are interesting. So let's do first QPE. You'll see later the details, but let me emphasize what this needs and what it outputs. So it needs the Hamiltonian in a certain way. In particular, you need to be able, if your Hamiltonian works on m qubits, let's say these are m qubits lines in a quantum circuit, so I need to be able to code, let's say, a gate on m qubits that acts like e to the I times, let's say, t times h for some t. And I need to be able to do this controlled by yet another qubit. So I'm assuming some qubit up here, and I need to have a gate, with this control symbol, meaning that if the top qubit is 1, this operation on the bottom qubits is done, and if the top qubit is 0, it's not done. So this is a non-trivial business, right? If H is your favorite Hamiltonian, it's not easy to make a quantum circuit that does this. In a sense, this is the whole problem to use QPE for something good. But if you can do this, so if you have that, the second thing you also need is some quantum state, which you're going to put here. So you start the bottom qubits, or the system qubits, in some state psi. What you need, so if you're after the ground state, say, you need a state psi such that there is an overlap of psi with psi ground state. Well, let's say call that C or C squared. What do I call that? C. And you want this thing, well, let me do it like this. C squared. And you want this to be non-zero. It doesn't have to be 0.999, but it has to be, a non-negligible number bigger than 0. So these two things you need. Some hunch at a state that has an overlap with the ground state, and then a building block of a quantum circuit that's this control e to the ith for various t's. If you have all that, what is the output? So what does the thing do for you if it's all built and run? So what the thing outputs is, well, first of all, it gives you E ground state in a binary encoding. So meaning that it's like a decimal notation in powers of 2 rather than powers of 10. I'll come to some details later. And it gives you that with probability equal to c squared. That's I guess to be expected. If your state overlaps by some amount with the ground state, you get this output with that probability. So let's say if this thing is 1 over 10, and you repeat the whole procedure 10 times, there's a good chance you've actually hit the ground state and found this E ground state value. And having done that, if this is successful, you also pick up the exact ground state itself. So you find E ground state, but you also find the exact psi ground state. So in a sense, the circuit projects on the ground state upon measurement, right? The circuit answers measurements, and there's a certain chance that you hit the ground state. If that happens, you pick up its energy and you pick up its state, and so that's perfect, right? Then you have exactly what you need. So this is a very nice method. You know what you get. There are some subtleties. For example, this binary encoding. If your number is not expressible in let's say a certain number of binary registers, you get an approximation, but that's all understood how well that works. So this is a very clean and nice method. If you can do it, it's the method of choice, I would say, and it works for you. And today I'll give a few examples where you see it happen. I hope I can put it on the screen with a bit of quantum coding that you see it in action.
Sorry, I didn't get it. Is this a sort of variational idea that you start from a psi which is not too bad and then you improve it?
It's not variational. It's actually the next thing. So it's the only thing I need is that there is some overlap, and then what the circuit does, it projects my state on the exact ground state. Whereas, you know, with a variational scheme, you try to come close as you get by, you know, putting the right value to all kind of angles.
Psi is a test state.
It's like a guess for the ground state. Your guess.
Yes.
And what happens, you know, with probability c squared, the output of the whole thing, the whole circuit, will be the ground state itself, sharp, and its eigenvalue as well. So yeah, believe me, it's coming in 10 minutes, how this goes.
But c squared will be very small.
That depends.
When you take
so you need like a pre-processing step to get your hands on a psi that's you know, not negligibly overlapping, and that's an art by itself. So you can do adiabatic evolution. There's clearly an issue here. I'll do an example today where I can guess the psi with my eyes closed, because it's a small example. But in the big scheme, this is one of the issues, right? One issue is to code this controlled unitary, you know, without too many gates needed, and the other is to get your hands on a good psi as input. So nobody says this is easy, right? It's work to make these things happen, and it's obviously extremely hard to beat other methods in supercomputers as we know them. Okay, other method is VQE. It's a completely different strategy. I'll come to that today, but let me just mention what this needs and what it outputs. So it needs what I would call a parametrized trial function. Or trial state, if you wish. Wave function, same thing. So let's call that psi trial. And that comes with some angles. So that typically it's theta 1, theta 2, and a whole bunch of them, theta s. So I didn't have those angles over there, right? But here I have them, and they're essential. And then I need also, another need is, you know, I have to be able to represent my H as an operator on the circuit, which typically means that the H is in the end represented by some sum of Pauli words. So for example, it could be A1 times X1, it could be, let's say, B1 times Y2, Z3, plus ... So there is some basis for representing, say, my molecule or my Hubbard model, the thing I'm trying to understand. And I have to do all kinds of mappings and things to express my Hamiltonian in that basis. And in the end, that gives me some expression which I can put into the circuit and measure, essentially. I can measure term by term. So I can measure this term, etc. Okay, and then what VQE does, so this is what the needs are. If this is all available, then what it outputs, well, this you know variational methods in quantum mechanics. It outputs an upper limit to the ground state energy. So you do get an upper limit to E ground state. But this is guaranteed by general principles. Nobody guarantees how good that limit is, how close you are. So clearly, the strategy is, you know, the circuit is going to so to have a piece that generates this trial wave function. So there's going to be a quantum circuit with all kinds of angles in different places, and it prepares this trial state. Then I do quantum measurements of these operators, and I collect all the answers, add them up, and that gives me the expected energy on that trial state. And then I go in a loop with optimization. So I change my thetas a little bit to try to get this energy lower, lower, lower. And when that's all done, I've optimized my assets, and I'm guaranteed to have found an upper limit to E ground state. It's probably not exact, unless I'm extremely lucky. Okay, that's different from the top scheme. This is an approximation, but of course there's an art to this. If you skilled in writing the right kind of trial wave function over here, you can hope to get very close, to come very close. And that, again, that is a somewhat uncontrolled situation. You don't know that, but there's all kind of, you have to build up experience and see how well this works for you. And then you could say, well, this I can also do on a classical piece of hardware. This whole procedure is why do we need a quantum computer? Well, the thing is, these trial wave functions, it's easy on a quantum computer to generate highly entangled trial wave functions. As opposed to, if you do classical maneuvering, you can write product functions and you can put in a bit of entanglement. But quantum computers with lots of C-knots and Toffolies and stuff, they easily generate highly entangled ground states that could be the ones that you're after. No, that's yet another thing which I'm not bringing up here.
Okay.
Yeah, it goes as VQE. I think that's pretty much standard. And then it has all kinds of sub-names. So tomorrow I'll be talking about, for example, HVA, which is Hamiltonian variational ansatz, and there's a whole tree of things. But I guess the general group of ideas is this thing here. And clearly it's an art. So you have to in particular, generating your H, that's simply work. So if you want to do, let's say, some molecule, you do mappings, and then that gives you this H. So that's simply work. But generating the right kind of trial wave functions, that's an art. And if you're good at that and you have a big size machine, you can hope to be really accurate down here and approximate your targeted quantities really well. Okay, so that's the two things that we have, and that you see if you look at papers, quantum chemistry on the quantum computer, it's always about these two things. And it's comparing how well does this perform, how well does that perform, how does that extrapolate to future systems, etc. Typically, VQE is easier on a small, baby quantum computer as we have them today. You can run these things, and people have done that on a few qubits to do a small molecule simulation. QPE requires, as we will see, quite a few more qubits and many more gates. So that's typically for later, when the machines are bigger and more accurate. But then it has its own appeal, so to say. Okay, so that was my opening story, and now I'd like to really use quite some time to talk you through this QPE. I'm not sure if people have seen it or used it, and if you have, you'll be a bit bored, I'm afraid. But maybe people haven't seen it, and this is like a first time. So I think it's nice to explain how this thing works and how you build up a bit of circuitry that does all these things. It's quite magical. Yeah, so let me leave these two things and start a new story on the left. And what I always like to do, and certainly when giving this kind of courses, is to go to the simplest possible situation of the new idea, so to say. So let me make the thing extremely simplistic, to the point that you may find it trivial. So let me assume the following. The H that I've been talking about all the time, it's 2 by 2 as a matrix. And it has eigenvalues equal to 0 and equal to 1/2. So you can imagine a 2 by 2 matrix with these properties. So this is guaranteed. And now the other thing which is guaranteed, so I get this, and I get a state psi. And I'm guaranteed that psi is an eigenstate of H. The only thing I don't know is which of the... So the question to be handled by my quantum computer is, is it psi sub 0 or is it psi sub 1/2? It's one of the two, and I don't know which one it is. So that's like a binary question. So I need 1 qubit, right? If I set up a circuit and I do a measurement, and then I can say if the measurement is 0, it was this one. If it's 1, it was this one. So that's what I'm going to build as a quantum circuit. That will be like a prototype quantum phase estimation thing. So yeah, let's see what we can do. Maybe let me leave this, so you know what we're addressing here. So the idea is, as I kind of told you in QPE, what you try to do is you have this, you take a qubit, which is like the system qubit, which is for the 2 by 2 Hamiltonian. And as I told you, you can imagine, you would say, well, let's apply h on that qubit, right? And then somehow measure, and that's the eigenvalue. Well, h is not a unitary. H is a Hermitian matrix. But so what I can do is I can do e to the ih. So let me do e to the 2 pi I times h. That's a nice time to run my Hamiltonian on let's say my system qubit. Let me call that yeah, why not q sys. So that I can do. And so what I know will happen, if you look at my two eigenvalues, if I put this, if I put my state psi on this qubit lag, somebody gave me psi, so I have it, I can put it there. Then you see what happens. This unitary gate will be trivial for if psi was the psi 0 choice, because then h is 0, nothing happens. But if it's the psi half choice, then this is e to the pi I, which is 1. So I'm building up a translation of my data, so to say, in circuit language. And now I've achieved that there's a -1 happening if it's psi half and not otherwise. And now you would say, well, let's measure this -1. So right, you can put a measurement gate somewhere here, let's say. But that won't work, right? Because if you measure that state, you'll find the psi back, and the -1 is not visible. It's a phase. It is not visible. So you can't do it like this. So you need some trick to pull this phase into another qubit state that you can measure to learn. And so the trick is the following. You bring in a second qubit, which is like the register where the measurement will take place in the end. And what you do there is you start, so it starts in the 0 state. And the first thing you do is you make it a superposition of 0 and 1. Now typically we use the Hadamard gate and we write h. There was an h already for Hamiltonian. So to avoid confusion, I write Had. Yeah, so remember the Hadamard gate was this one here. It's the 2x2 gate, 1/√2. So it's a unitary like this. Yep, and so maybe now let me actually give the whole circuit and then talk you through why it works. So the next thing I do, I'm going to do this controlled action of e to the 2 pi IH, as I already announced. I need that, so that this phase on the second qubit is kind of pulled into the first qubit story by this control action. I do another Hadamard gate on the top qubit. And then it's good enough, and now I measure. So I put this measurement. So this is supposed to be a measurement apparatus that simply measures my qubit in the standard basis. So I find 0 or 1. And now the claim is, if this measurement comes out as 0, I can conclude that what I was having on the left lower situation was actually psi 0. And if the measurement comes out 1, I can conclude that it was actually psi half, with certainty. Okay? So that's my claim. So let me now kind of prove the claim. So this needs a box. This is an important result. So proof.
Sorry, but what about the superposition?
I was promised at the beginning it's one of the two.
Okay.
Okay, and if not, you'll see both things happen with this c² amplitude. Okay. But I made it so simple. Somebody promised me it was one of the two.
Okay.
Okay. So now let's check this claim. So let's do the case. The case where my input state was psi 0. Now that's very simple, right? I told you before. If it's psi 0, this whole thing doesn't do anything. So nothing happens, so I do Hadamard, nothing, Hadamard, and since this guy squares to 1, I find, I've done nothing to the first qubit, it started in 0, so it ends up in 0. So I'm certain to measure the first qubits, I have the 0 state, so the measurement will give me the value 0. So that was easy, but now of course the meat is in the second case. So let's imagine we started as psi half. And let's keep track of what the top qubit is doing. So the top qubit, it starts in this situation, it starts in 0. It goes through the Hadamard gate, meaning it's 1 over root 2, and then it's 0 plus 1. That was easy. That's applying this gate to the 0 state of the top qubit. And now comes the subtle thing. So here is where it happens. I have a control action on the second qubit depending on what state my first qubit is in. So if the first qubit is in state 0, nothing happens. This control is not on. So that first situation, the 1 over root 2 times 0, that remains no matter what. But if the top qubit is in state 1, I actually run this gate down here, and since I'm in the psi half, this gives me a -1. Okay? So there something changes, so namely the plus times the 1 state becomes the minus times the 1 state. So here, this phase that's coming from this box was pulled into my top qubit state at this moment. And now you see, if I do another Hadamard gate, this combination actually maps to 1. And that's that you see over here. And if I'm in the 1 state and I measure the qubit, I find value 1. Measurement is equal to 1. Okay, end of proof. This is, and everything is certain. These are deterministic measurements. And this is the gist of what QPE does. This is a baby example where I only measure. So in a sense, I measure a binary in binary notation, and I can only see 0 or a half. But in a second, I'll make this bigger so I can see more digits and repeat the game. So this is quite beautiful, right? There's a multiplicative effect of your Hamiltonian via its unitary on some qubit. You pull that phase into the state of the top qubit, and by playing with Hadamard, you pull out the right eigenvalue.
I'm sorry, but it doesn't fit with the definition, right? Because in one case, C is equal to 1. In the other case, it's C equal to 0. So it really doesn't fit with the definitions you had there.
Yeah, so I took, cases where C is equal to 1 for one of the two states, but I could have, for example, started from the superposition of the two, psi 0 plus psi half, and then the outcome would be 0 or 1, with 50%, and you would still learn the eigenvalues. Mm-hmm. So you would see the two eigenvalues come in, and if you've seen, for example, 0, and you see what's on the bottom leg, which you haven't measured, that's in the eigenstate for that eigenvalue. So you only measure the top qubit, and the bottom one actually provides you the eigenstate of the observed eigenvalue. And again, in the easiest case, you prepare it such that you know you're in eigenstate, and then it's one number. If you can't do that, then you prepare some superposition, and you see different outcomes happening. Yes? Sorry?
What if you do not know the spectrum of H? I mean, in this case, we know, that's why we choose 2 pi as time, right?
Well, yeah, so with this one you learn very little. You learn 1 digit, essentially. But I'm going to tell you in a second how you make S digits. And then you get a binary representation of your eigenvalue in all cases.
Okay. So basically, the only requirement is that the ground state has energy 0, kind of.
Not even. That was just to make it simple. Any number would go. It's just that in binary notation. So in a sense, I'm using binary notation of the sort 0 point S1, S2, S3, etc. By which I mean the number S1 times half plus S2 times quarter plus ... Whereas the S's are 1 or 0. And if I give myself a single S, which is what I did over there, I can only represent 2 numbers, which is a half and 0, which is why I took that example. But now I'm going to do 2 acids, just to build, and now I can do 4 numbers, right? Half, 3/4, etc. And then if you allow yourself S qubits, so let's say 10, and then you do a fine-grained search. And you'll be certain in that case that the outcome, the digital outcome of the measurement is a good approximation to the eigenvalue that you're after. So yeah, I decided to actually do a second example with 2 digits to I guess prepare the way for the general statement. So let's do that. So now I'm going to put 2 of these top qubits using a Hadamard like this. So there's a bit of an art in drawing this circuit. I hope it comes out right. So these are my 2 qubits. They're going to represent, as I just explained. So there will be an outcome to the measurement coming from these 2 bits, and that will give me a digital number 0.S1 S2. And that will be the representation of my eigenvalue. So I need 2 qubits to do that, and these are my 2 qubits for that, 1 and 2. And then, there's my system, where the Hamiltonian acts and the unitary it makes. So that's, again, a whole bunch of lines, depending on how big my system is. And then, I can make the unitaries. And I'll do this twice, so there we go. Now comes the trick. In a sense, I have to treat S1 and S2 separately, so that I have both of them in action. And the way I do that is that for the S2 line, I'm going to control this unitary e to the 2 pi I h as before. So that I glue to line 2. And then to do line 1, somehow, I need to play with factors of 2 to get my binary number build up. So what I do is I'm going to actually use the double time here. I do 4 pi I h. So that's my circuit. I run it. So I know here goes my state psi with the same story. It could be an eigenstate, it could be a superposition. And and I measure in the end. Here are my measurement gates. This one and this one. So outcome, a number S1. Yep, that's the top, and a number S2. And those 2 numbers I feed into my expression to get a binary number for my eigenvalue. So I keep saying eigenvalue. Of course, we're measuring phases, right? So we're measuring h modulo 1. If I do it like this, that's clear because that's all you can do using these unitaries. So this is the proposed circuit for the for the case with 2 digits. And having seen this, you'll be able to generalize to S digits without any problem. The question is, how do we complete the circuit? So actually, sorry, I was too quick here. In the case that I just erased, there were additional Hadamards over here. And so there has to be something done over here before we measure. That was extremely important, and I forgot that, sorry. So there is going to be a thing we need to do here to make this whole thing work. And we have to discover what that is. So let's see how this goes. So, so let's imagine, the eigenvalue for this state over here, let's call that E. And let's assume, E can be written as, if you wish, 0.E1, E2. Or if you wish, E1 times a half plus E2 times a quarter. So that's my E. And with that, I can look at the top 2 qubits after, before my question mark box, but after having done these control unitaries. And what I have, so the output at that moment, so let's say the intermediate state before completing everything. So what I mean, so the state, when when I've come to this point in time. So that state. It looks like this. So I have a 1/2 because of 2 Hadamars give me 1√2 factors. The second qubit, the following happens. So it's the 0, 2 plus the 1, 2. But if it's the 1, 2, I controlled an action on the bottom stuff, and that gives me e to the 2 pi I times e. The first qubit, so this is like tensor product notation. Same story, it's 0. And then there's this double phase, 4 pi I E 1, 1, like this. So that's my state for the top 2 qubits after having gone through the first part of the circuit. So in a bit nicer notation, I could say, well, this is like a half. And now it's the sum over x1 equals 0, 1, and x2 equals 0, 1. Right, there's 4 terms, the basis for these 2 qubits. And then what I'm looking at is the state, let's say x. So x coded by these 2 x numbers, so that's 0, 0, 0, 1, 1, 0, 1, 1. And then there's a phase in front, and that phase I can write as e to the 2 pi I times e times x, where x is now 2x 1 plus x2. So I do a binary coding of my x in the usual way, not as a fraction, but as a regular number like this. And there's a binary coding of my energy in the fractional way. So this is what I have. Okay. Now what I'd like to have is this thing here. Right? So the question box that is still standing there should do the following thing. It should map this intermediate result to, well, this state here, the E1, E2. Because if it gives me that state and I measure, I'm pulling out these 2 numbers, and I can build up my eigenvalue, 0, quarter, half, 3/4. So I need an operation that sends this thing to that thing, where again these 2 e's are hidden in my e in the exponent. Okay, so I need this, and then there's a way to go back. Now, if you look at, if I start from here, going from here to a thing like that, that looks like a Fourier transform, right? It is a Fourier transform. If you think this is K space, so this is X space, then this is like a discrete Fourier transform. It's a quantum thing, so this operation from right to left is called QFT. So which, for a change, is not quantum field theory, but quantum Fourier transform. And so what I need in my question box is the inverse of that thing. So I need QFT inverse. And the claim is, if I do that, so if I somehow make sure I can make this QFT inverse as a circuit, which I can, and I put it in that place, and then I measure, outcome, maybe I should say E1, E2, that's what I used so far. And my energy value is going to be E1, E2. This is my E in binary coding. Okay, so if this, I have to tell you a little bit more about this QFT thing, but now it's done, right? So this is what we achieved for 1 qubit, now we do it for 2 qubits. So, here goes the state that has energy E. Here we do certain things to 2 qubits, and then in the end we measure, out comes E1, E2, we make this number, and that's the eigenvalue. And the eigenstate for that, sits right here. So the state that is not measured, but still available for further use, sits on the bottom lines. Okay, so nice. And to wrap up, let's check what this QFT thing is doing. Yeah. And I took this small example simply to be very, very explicit so you can see it in action. So if you look at, if I make a table, so E1, E2, if I put that here on the top, so that's, 0, 0, 0, 1, 1, 0, 1, 1. So doing QFT to the E gives me that superposition that's over there. So that I can write as a sum in the X basis. So there's the X basis, so X1, X2, which are simply called X over there, same thing. And that has, 4 basis vectors, 0, 0, 0, 1, 1, 0, 1, 1. And I can make, this table, if I start from this thing, how do I build up a sum of these terms here? So now let's put in the numbers. If it's this here, the exponents are all 0, so I get 1, 1, 1, 1. But now let's suppose that I do this here. So this is, let's see, E2 equals 1. If that's what I have, so let's see this exponent that I'm looking at. So the E times X is half E1 plus quarter E2 times 2x1 plus x2. Yep, so if I do the E2 equals 1 thing, it's a quarter, which means that I have an I here, a -1 here, and a -I here, and a 1 here. And now you can kind of see what happens. Sorry, this is wrong. No, sorry, it's right. It's like this. This is like -1, 1, -1, and this is -I, -1 plus I. So this is my matrix with a 1/2 in front. So this is my QFT map as a matrix in the case with two dimensions, or 4 dimensions, 2 qubits. And now I guess it's all clear, so now I have one more blackboard to wrap it all up. If I have the general case, so I do this thing not on 2, but on, let's say, S qubits, then I'm looking at, so let's say, QFT as an operation, or if you wish, a quantum gate on n qubits. It's going to be the matrix. Well, okay, what it does, it sends, some basis vector, which I now call K, which is the same as what I called E before. It sends it to a matrix Fn on that same vector K. And what is that matrix? So n is 2 to the n in this case. So that matrix is 1 over, let's see, 1 over the, what is that? Because the root of 2 to the n, right? Yeah. And then it's, well, sorry, let me be even more explicit. So this matrix on that K I can write in the usual way as a sum over an index. So let's say J equal to is 0 to n minus 1 of omega n to the jk times k times j, sorry, like this, where this 1 over root n, where the omega that I need is obviously the number omega is e to the 2 pi I over n. Yeah, that will be it. So this is the QFT in general terms. And this is the version with only 2 dimensions. And my circuit in general, if I do not 2 but n lines on the top here, needs the big QFT inverse as a matrix. And then it all works. Okay, so as a kind of as a byproduct of this analysis, we discovered a new quantum gate that's nice. So it clearly has a function in this circuit. The only way to make this happen is to use QFT inverse. You may know that some of the other famous quantum algorithms also hinge on QFT as the magic that you do. In particular, this Shor factorization of integer product of two primes. If you look at how that's built, the key of what happens there sits in a quantum Fourier transform step. So it's a magical thing, and the thing is, you know, it takes quite a few gates to compile a QFT in standard gates, but not so many. So not really many. It's not exponentially many. Whereas, you know, the thing is handling a space that's exponentially big, 2 to the n dimensions, right? So it's a very big operator that you can build relatively cheaply, and that way it's a magic thing when you're building quantum computing circuits. Okay, so I prepared like a little demo in Circ, but I think it's probably good to wait with that till after the break. So let's do that. Come back at 2 or?
Yes, if there are questions, please, now, or then we take a break and reconvene at 2. You have a question? If there are questions in the lecture room.
It's a very stupid question. Just why is that called a quantum Fourier transform and not just how is it different from a usual Fourier transform?
Since I guess the formula, so you can read with classical eyes, but the idea is that, you know, this thing actually, you know, you want this thing as an operator on a qubit register.
Okay, but I mean the unitary matrix you wrote is just the
it's the discrete Fourier transformation. Yeah. So you want the quantum gate that has as its matrix representation, you know, the discrete Fourier transformation. That's what it is.
Okay.
Another question maybe. I was wondering, there's also a question in the chat before if you want to answer that.
I think if you do, for example, a C0 count, it's polynomial in, I think it actually goes like n log n or so. So the number of those that you need is relatively small, certainly not exponential. I don't have the figure ready, but it's, I think it's like n log n that you need, so it's a decent number. So I guess in applying QPE to, you know, a serious problem, the bottleneck is not the QFT part. The bottleneck is this controlled unitaries and the input state that should be overlapping decently with the ground state. These two things are different.
Okay, so am I audible?
Yes.
Okay. So I was wondering what happens and how can we detect, for instance, the generate states. For instance, if we're searching for a ground state and we have the generate states in this setting.
Sorry, I heard you want to generate. Sorry, you want to degenerate states?
Suppose yes, in my spectrum I have a degenerate ground state, or I'm targeting a degenerate state with this. Quantum phase algorithm. Will that work?
I guess it still works. Right? If your input state has an overlap with some of those, you'll pick up those eigenvalues. So I keep saying ground state energy, but it's completely general. So whatever eigenvalues are contained in this input state via superposition, they are going to pop out of the circuit via measurement, and they could be all kinds of values.
Okay, so in general, I will. The question was, how can I distinguish? How can I detect the fact that I have a degeneracy, for instance, because I will get the correct eigenvalue, but can I run it multiple times from different starting states, initial states, and detect degeneracy in this way?
Yes. So I guess the question is, how could you detect using this business that there's a degeneracy? So, you know, if you see a certain eigenvalue pop up multiple times, is the system hiding degenerate states? I would imagine you have the state. So, having seen this eigenvalue, you can keep working with the state and measure it in some way or other. And this way you can discover if it's always the same state or if there's multiple states contributing to the eigenvalue.
Okay, thanks.
Yeah. Okay, let's stop now and reconvene at 3.
Okay, so my plan for now is to run a bit of this quantum programming code, same system that I used last week for some small things. And so I simply programmed these kind of circuits in 2 simple cases, 2 choices for what H is. And I hope to demonstrate to you that things work as I promised. So I took the risky version, so I deleted all the output, and I'm planning to generate it back in front of your eyes. I hope that works, and if not, you'll have to consult the printed version of this thing. But let's see. I hope this works. So there is this, a bit of code that I prepared. First thing I do, I import. This is Python-based. I import all the circ commands to run qubits. A plot program, which I don't think I even use, and then a funny line to allow my circuits to keep going to the right without, line breaks, so to say. So there we go. So now it's thinking. Yeah, that looks okay. Okay, so now I'm going to prepare a few qubits that I need to build my circuits, and I give them a name. That's easy. Okay, then I make this QFT inverse. I didn't go into that, so there is a quantum circuit that does this whole thing, right? Would have been nice to explain with you how you do that. I simply took it from the books, or at least from some circ manual, and I put it here. So you'll see it show up on the circuits, but for now it's without explanation. Maybe it's a nice exercise for today to figure out that this is the right thing. So I'm simply loading it as like a subroutine, so I can use it. Yep. Okay, so now comes my first example. Again, I try to go to the smallest possible. So very similar to my first example 50 minutes ago. So I take, if you wish, so the unitary that I put over here, take z to the power 2 theta. 2 theta. And if, as a matrix, z is 1 over here, so that's simply 1. It's -1 down there, that's e to the pi I. So down here it says e to the 2 pi I, and then theta. Right? So this, if you compare to here, this is where h sits, or what I called e before, so now I call it theta. So I'm going to build a circuit that measures this theta. So I input a control version of this gate, which I call u. And what my circuit should do is measure my number theta that sits here. And that's like the baby example of this whole scheme. So I do this thing, and now I have to determine what my accuracy is. So how many of these lines over here I want to have. So I said I choose 6, so I'm going to measure to 6 binary decimal places. Okay, that's just a choice. Actually, yesterday you won't challenge me how much can your computer handle, and we put 16, I think, and everything still worked. So you can go bigger. Okay, and then I picked a theta, just to be explicit. So I took it to be half plus 1 over 8, 1 over 32, 1 over 64. That fits in my size 6 register, and that's the number down here. So we should check that our quantum circuit reproduces that number. So keep that number in mind, and it should come out later when we do things. So okay, now we start building the circuit. And if you look what happens there, I should use my cursor, I guess that's easier. I simply build the part where I do these controlled U operations, and I do these Hadamars. Right here, I put the Hadamars on the top lines, and here I do the controlled operations on the bottom line. And then I make a print so I can see what I have. And you see that looks pretty good. So you're looking now at a circuit of the type we've been discussing, there's 6 lines to store my binary number, and there's only one system line, so to say, which is a two-dimensional space with this U as its operator. And so all these powers of U, you know, recognize certain gates. So it calls them Z and S, those are all powers of Z. So those are the right things. What I should now do is add my QFT inverse and the measurement gates. So that's the following command. So now the circuit is expanded, and now what you see in the top right corner, so to say, of the circuit are lots of gates, and they together constitute this inverse quantum Fourier transform. Okay. Again, I didn't go into the details, but all those controlled phase factors that you see there represent QFT inverse. Okay, and now there's one more thing. So actually, let me run the circuit as it is now and see what happens. Actually, let me quiz the audience. If I run this circuit as it stands, what will be the output? Am I going to see my number theta points blah blah blah? Let's do it. So I run. So I essentially measure my qubits. So there's this you know, sim.run measure blah blah blah. I do it 5 times, and then I print the theta that comes out as the binary number, like this. So now you see the measurements of the individual bits came out like 0, 0, 0, 0, 0, 0, 6 of them. Second time, same thing. So I was measuring theta equals 0 all the time. Yeah, so this was to be expected, right? Because, you know, as I told you, there should be an input state on the system qubit, and I didn't bother to actually write that, which means the program puts it in 0. So I was actually considering the qubit down here in the 0 state, which means that the unitary was like this, it didn't do anything, and it measures theta equal to 0. So to actually hit my theta, I should make sure that, let's say, at this position in the circuit, I add an X gate. I flip from 0 to 1, so I'm in the right position. So let me do that. So that's what's the thing I skipped, takes care of that. So it adds an X gate right here, so in the beginning, and with this it should actually happen. Now everything should be fine. So let's run the whole thing again. And now you see it does work, right? So now the measurements, I do it 5 times, but I could have done 1 time because it's exact. So you know the qubits come out as 1, 1, 0, 1, 0, 1, and that means the number is this number. And that's exactly what I put in at the beginning. Okay? And again, I can do 1 repetition to make it less cluttered. It's the same thing. I measure once, get my number, and it's completely perfect. Now, maybe to answer a thing that Andrea brought up, suppose you know I'm not smart enough to completely fix my bottom qubit in state going with the eigenvalue. So, for example, suppose I add an extra x. Let's do that. So I add an extra Hadamard, let me do that, an Hadamard to my bottom qubit, so I put it in superposition and see what happens. Okay, so I do another insertion of a gate. I take H, I think this should do it. Yeah, so now you see there's an H and an X. So now my bottom qubit is in superposition. And now what you'll see is that the measurement either hits, you know, the 0 eigenvalue or the 0.61 blah 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 eigenvalue with equal amplitude, probability. So let's see if that happens. So now I should do repetitions. Let me do, you know, 20 repetitions. So these are the measurement strings, and now you see the actual theta value is 0, 0, 0.67, 0.67, 0.67, 0, 0, 0. So half the time you hit the one, half the time you hit the other. And it's precisely what we expected, right?
Yeah, thank you. So probably very stupid question, but I don't understand what the repetitions are.
So yeah, the thing is, I have my circuit, and the only thing I can do is, you know, measure the qubits. And so let me put it back to 1. So if I measure the qubits, and I do this once, then I can report the outcome. You know, those are 6 numbers, and in this case they're all 0. Yeah, repetition simply means I do it again, again, and again.
As in a real quantum experiment.
Yeah, so I have to rebuild the circuit, you know, reinitialize the circuit and do it again. So I have to
Okay,
repeat the whole procedure. So yeah, you're right. I mean, if I've measured, I cannot measure again. So it's not that I repeat the measurement as such, because then it repeats. But I simply re-initialize the circuit and I do it all over.
Yes, as in an experiment.
Yeah, and so there is this probability amplitude, so to say, for hitting things. If in this case it will be 50, so if I repeat the experiment 20 times, I see a distribution of outcomes.
Okay. But this is, I mean, this is a classical simulation of a quantum
Yeah, but
experiment.
so my laptop, emulates, as they say, exactly what the circuit would do. So it has a random number generator, I guess,
but it could also just give you the exact state.
Actually, so Circ allows you to do shortcuts that are not possible in a quantum experiment. So, for example, I can say, give me the state factor and stuff like that. But this is like the actual, how it would look in an actual experiment. So you measure and you measure again and again and again, and you build up a distribution.
All right. Yeah.
And so now maybe one more thing that I mentioned, didn't discuss much. Suppose we build a theta value that doesn't quite fit in 6 decimal places. So for example, if I add, to my theta, 0.0137. So now it's no longer a nice binary digital number, and I can still run the experiment, see what happens. So let me see, I think I can do this. So now the theta is another crazy number, but it's not as nice. So we can't expect to find this number back because we don't have enough binary digits to represent it. But let's see what happens now. So I rebuilt my circuit from scratch. I add the QFT inverse. Now let me put the right initial X gate so I'm in the second qubit and not have this mix. So now, you see, I'm sure to be on the bottom line. So I'm only going to see this thing here, not a superposition with 0. But I have this difficult theta value, which doesn't fit in my register. So now let's see what the circuit does, because it is in some kind of trouble now. So if we do the measurement, let's do it many times, because that's probably useful. Let's do it 20 times. So you see, what comes out is a number that's close to my theta, but it's not sharp. It can't be, because I can't express that number in this way. And also, it's not always the same approximation. So there's a bit of spread around this number. And so this is like the compromise that my program makes to approximate a number that it can't write. And it has, there's a certain probability distribution of how that goes. So this is more the realistic thing, right? If the number isn't a very special number, this is the kind of thing you see, and you have to live with that. And probably what you'd like to do if you see a thing like this is you add a few extra digits. So you get less fluctuations, because the fluctuation is always in the tail, so to say. The first few digits are sharp, and then there's a bit of uncertainty. But that's part of what you do. Okay, so I think that's pretty much what you can do for the one qubit system case. But now let's do an actual, interesting quantum system, which is the Hubbard model. So now I should maybe do a few things on the blackboard first. So then I guess I stop this and you activate that. So I'll come back to this in a bit, but let me prepare a few things before showing this. Yeah, so I'm gone, and now the camera comes back up. Yeah, let me. So let's talk Hubbard model, and let's try to do a little simulation thereof. Okay, so here comes my Hamiltonian H Hubbard. I'm sure you've seen this, minus t. Okay, and I make it small. I look at two, just to make it manageable. Two-side Hubbard model. So side 1, side 2. So what's my Hamiltonian? Sum over the spin states, and then I hop from 1 to 2 plus conjugate, and I do that for both spins, like so. And then I add the Hubbard U, and the way I like to do that, sum over the sides, the up occupation number minus half times the down occupation number minus half. So with this notation, it looks nicest, but it's just a convention of writing it like this. So this is, I guess the classic Hubbard model. So I said, I'm going to look at two sites. So there are some very simple states. For example, you put two particles, both have spin up and they can't move, and it's obvious. So the interesting subspace where things are not completely obvious is the one with two particles. So let's say f fermion number equal to 2, and also let's say sz equal to 0. And in that subspace, there's 4 states that I can write. So there would be up and down. So this means side 1, side 2. I can do down, up. I can do both particles on the left side and then an empty right side, or I can do this, right? So there's 4 states, and that's nice because now I can use 2 qubits to represent my little problem. The matrix for this Hamiltonian on that basis, this is all very simple, right? But I hope you appreciate that it's an example for running our little quantum code. So this matrix is minus u over 2, minus u over 2. That's the state without pairs, and then the state with pairs of plus u over 2, plus u over 2, 0, 0, 0, 0. And then there's a whole bunch of hoppings. And that's it. So this is H Hubbard on this 2x2 basis. So yeah, that was easy. Maybe let me keep the circuit, but make room over here for the. So we're going to ask our quantum phase estimator to diagonalize this matrix, right? That's the plan. But I can give away the secret of what comes out since I did it at home. The eigenvalues of this thing here, eigenvalues. They are plus or minus u over 2. And then there's a more interesting value, plus or minus 1/2 square root of 16 times t squared plus u squared. So you have to believe me there that this is the right thing. Now, to make this fit nicely in my quantum program, I make a certain choice, namely, let's choose u equals 3/4 and t equals 1/4. And I picked those on purpose to get nice numbers, because in this case, my spectrum is going to be plus or minus 3/8 and plus or minus 5/8. So I took a Pythagorean triple, I guess, to get these numbers like this. So that should come out. Another thing, I'm preparing for running this show here with that H in these boxes. We should also put a psi here. And we don't know what it is. I mean, of course, I can compute it, but so I would say, propose, we're going to put an approximate psi here that is a bit like the ground state, but not exact, and then we don't need that. So I would propose, with a bit of physical intuition, since u is positive, the system likes to stay away from local pairs, so it will typically use the left 2 basis states, which we represent as 0, 0, and 0, 1. In the qubit basis, so this is the qubit version of that basis. So a nice guess for starting the system off would be to combine these two and leave these two away. So I would propose we do the following. We start the system off in a psi, which is this thing here. So it's not going to be exact, we know that. This is not the eigenstate for those eigenvalues, but it should have a decent overlap with the ground state, which is the minus 5/8 value over here. Yep, so yep, I think that was what I needed for preparations. Yeah, so now I'd like to do the switch again, so I'll kill this, stop this share. I'll open my share.
Sorry, why the ground state is minus 5/8? Because U is positive, right? So, I thought that maybe the first two were ground states, no? This is too naive.
No, I guess, yeah, since U is positive, you like to be sort of in the left upper corner, so those two states, which have potential energy minus, what is it? Minus 3/4. And then the mixing via kinetic terms, they produce these two split states. And the 5/8 is the lowest.
So the kinetic term favors decrease the energy, that's the point.
I guess so, since I took T, I put a minus T, right? So there, and then if I take T positive, I may have mixed that up. I think my code is going to produce the plus 3/8 and plus 5/8.
Okay.
But, you know, you can handle that.
Okay. So maybe
yeah.
the value of T is not really physical, but okay, that doesn't matter.
Yeah, so let's make sure we see these numbers up here.
Okay, sure.
Yeah, also we're going to measure numbers modulo 1, right? So we won't see the difference between plus 3/8 and minus 5/8. So that's a bit of a coincidence, but that happened. Okay, so here is, so I'm going to build a circuit like this here, but now, you know, I have to handle this situation with H, you know, that matrix. And now I'm in a bit of trouble. You see, what I should do is produce a quantum circuit with C knots and 1 qubit rotations that represents this thing here. I could have done. So I took a shortcut, and I'm confessing that to you here. So I took a shortcut. So I simply computed, you know, on a piece of envelope the exponent of this matrix. So you know, so U hub. That's I guess, yeah, it's e to the I alpha times this H. And so I used a few auxiliary matrices to do that. You know, you can all do that at home, and then you find some combination of 4 matrices with all kinds of cosines and sines and e to the I alpha t things. So I simply did that. And again, it's a shortcut to what you should do, but it's just for illustration purposes here. So I made this U Hubbard. Yep. So for example, if I take this, well, take some choice. It's a matrix. Here's a little check. So if I do it and do the inverse to the dagger, and I do the product, I better get 1 because it's a unitary. So I did that check, and you see it happens. So the product is, this is the unit matrix in Python notation. So that's good. Then I actually define this situation here, which I call Hubbard layer. So it's a layer in my circuit. It needs an alpha, which is an alpha and, yeah, sorry, so what I call, yeah, so the alpha, that would be like 2 pi I guess, over here. And then it needs the U and the T for the Hubbard. And the bit is the number of bits that are in play. So I think, what did I do here? I put n equal to 3 bits, I think, for, no, I didn't do that yet. I should do it in a second. So, but here is this thing. So now I can use it. So now I go to the U equals 3/4, T equals 1/4, and expect these eigenvalues. I do 3 bits. That's just a choice. That's enough to store these numbers. So I built a circuit, and there we go. And now you see what the circuit does. It's nicely represented. It's a control U Hubbard, where U Hubbard, you know, concerns 2 qubit lines as a 2 qubit operator. And you see the first time the name is 2 pi I. As you can see, that's exactly what I should do. That's the 2 pi I. And the second time it's 4 pi, and the third time it's 8 pi I. It's not 246, it's 248. So that's what I do. And then, you know, I add the quantum inverse Fourier transform. That's happening here. Actually, I guess here you can see a bit better how that looks. So if I scroll to the right, so you see this is the quantum Fourier transform on 3 lines. On 1 line, it's Hadamard. I showed you that. On 2 lines, it's a bit simpler. And this is all you need on 3 lines. So this piece here is quantum Fourier transform on 3 lines. So that's that. Okay, then I should make sure my left initialization of the system is okay. And I had this plan to do it like this. So I can reach this here by putting an Hadamard on the right qubit, which is the bottom qubit, I guess, for me here. So where did I do that? I didn't. Yeah, so I do it here. So this is inserting a Hadamard, this thing here on the bottom qubit, like this. Yeah, so there it sits. So now it should be okay. And now if I run the circuit, I would hope to pick up those numbers, right? That's what I prepared for. So I repeat 10 times in this case. And you see what happens. So yeah, you see you get these two numbers. And actually, as I said, I was kind of clumsy enough to choose one to be, well, modulo 1, they're the same numbers. So you only see 2 and not 4. And the thing is actually dominated by the 375, which is the same as the -5/8, modulo 1. And that's the ground state, right? So the 375, so let me actually, you know, these numbers here are represented. This is, you know, 0.375 for the plus, and the minus would be the 0.625, and the same here, yeah. So this would represent plus 3/8 and minus 5/8, and this would represent minus 3/8 and plus 5/8. And again, we're expecting that this guy dominates because of the way we initialized the state. So we're expecting that 375 dominates, and it does. But it's not always, right? So there's a certain chance that you hit the other value. Yeah, and if you, yeah. So if I now, just to illustrate this, there's a question or?
Yes, sorry, so the probability that you get one eigenvalue or the other, can you relate it to the, I don't know, the overlap between psi and the different eigenstate or something like that?
Sure. So I guess the probability of, for example, you know, the chance of hitting the, let's say, the +3/8 would be the overlap of my initial state, which I prepared with this Hadamard in the corner, with the eigenstate going with 3/8, right? And then there's 4 formulas of this type.
Squared, probably.
Squared, yeah.
Okay, yeah. Okay,
and
thanks.
so there's, you know, it includes the P minus 5/8, the ground state, which would be, yeah, same thing. So the psi minus 5/8. And, you know, with my bit of physical intuition, I tuned psi so that this is the biggest of them all, which is why I see the number 0.375 most of the time.
Yeah, okay, thanks.
Yeah.
And here, of course, you picked your example so that all eigenvalues are multiples of 1/8.
Yeah, so indeed, since it's 1/8, I can get away with only 3 binary decimal places, so to say.
Yes.
Which is why I stopped at only 3 lines up there.
Yes, exactly. So then you take more generic eigenvalues, you will get also some fluctuations.
Yeah, shall we try? So suppose I do it again, right? So what would you like to see? Another U or another T, or so? For example, what shall we do? Shall we make T bigger? Well, let's make T bigger. So let's do 1/40 instead of 1/4, and let's interpret this C. So here's where I do that, right? Here I insert my things in the circuit. So now I build a new circuit where you see the T is now down by an extra factor of 10. So it's a different situation. So my estimated psi should be even better now because I'm doing very little kinetic terms. So now I make the circuit, I add Q of T inverse, I initialize on the same thing. And now let's think before we run it what happens. So now there will be 4 different eigenvalues because this accidental degeneracy is gone. And one of them should dominate quite strongly because my initial state should be pretty decent to represent the ground state. So that's what I expect. But there's one more complication. My actual eigenvalues won't fit in the 3-digit register because there will be some crazy number, right, with square roots. So there should be a bit of confusion because we'll see numbers that are not all the same. So that's to be expected. Now let's do it. Yeah, that's a bit surprising. No, it's not so surprising, I guess, right? So I guess, yeah, so what we're looking at, you see, we kept u at 3/4, meaning this is very close to 3/8, and that with a minus is what we see here, right? So that's, and, sorry? Bigger T, okay, bigger T. Yeah, it's very easy to take requests. So what T would you like, Andrea? Okay, so T equals 1/2. Then we get a new situation. Yep, circuit, inverse Fourier transform, initialize the system state, run the whole thing. Okay, so we put more digits. Yeah, it's why not? Let's put how many? Let's put 8 digits to get a better story. I hope my computer can handle that. I think it can. So the same parameters, but now with much more precision. Run the initialize. Oops, sorry. Yeah, that was good. Sorry. And now I do it. Oh. Yeah, so sorry, that's the risk of doing this real time. Let me try once again, and then I put 8 bits. I do this, I do this, I do this. Yeah, okay, now it worked. So let's see. This is what we get. I think the trouble is, you know, we should read these numbers modulo 1, right? And I think now the ground state energy is below -1. So we have to fish among all these things which one it is. So it's clear two values are dominating quite clearly. So this is 0.06 and there's this 0.93. And that's what we have.
But so the first two should probably correspond to the same eigenvalue, right? The 0.92 and 0.93.
Yeah, that's quite possible because, you know, we have a number that doesn't fit in the register, even though we took now 8 or so. What is it? Binary places. Yeah, but you know, you can clearly play with this and learn things. Yeah, that's simply how often I did this. Yeah, so that should be coming from these kind of numbers, right? So there's four probabilities, and they each come with their own eigenvalues, and so we should, in the end, you know, should always see 4 numbers with a bit of rounding because of the register being too small, and the probabilities by which they come we can manage by playing with what we put there. Okay, so but you see, I guess the thing works nicely. Yeah, so maybe I'll do one more time this switch. Yeah, like 5 minutes, then my story is finished for today. Can you do this? Yeah, so because, you know, I repeat again that I cheated big time by not coding this thing for two-sided Hubbard, but by actually simply typing the matrix that I computed by hand and telling the circuit to do this. I mean, you cannot tell a quantum computer to do that. You can only tell circuit to do that. So to make good for that, let me give you one tiny step in the direction of actually compiling these kind of gates on hardware. But I should say that doing that for two-sided Hubbard, actually I did a bachelor project with a student with as the assignment that she had, you know, actually compile the two-side Hilbert situation in basic gates. I make a circuit and do it. A technique called qubitization, and it was a nice thesis, but a whole book to handle that carefully. So one little remark is the following. If I go back to the first example, let's say the example 1, there the only thing we needed was this controlled gates of the type z to the 2 theta, right? Or maybe to the 4 theta or whatever. And already this, this two-body gate is not in the standard library of C0 and qubit rotations. Okay, because it is a controlled rotation, and that wasn't in the books. So now let me give you as a little fact how you can compile this one. So there will be a task, compile this circuit in C0, 1 qubit rotation, and nothing else than that. And that's actually very easy. So let me give you, those are these little tricks of making circuits that do what they should do. So in this case, it goes like this. It's kind of funny. So I put my z to the 2 theta as I want it, but now it acts, uncontrolled. So now it rotates everybody, but it's supposed to only rotate the 1 state and not the 0 state, right? Because it's a z to the power something. So I should rotate back the 0 state. So how can I do that? Well, if it's, I go like this. So if the, do I do this right? This is what I prepared at home. Let me check if it actually works. So if I do this, let's see, if the top line is in the 1 state, I think this is maybe too quick, or so the plan was if the top thing is in the 0 state, nothing should happen. Which means that so I guess I need another x here. Right? Because now if the top state is in the 0, it becomes 1, and the 1 flips this guy here. Am I making this too complicated? Let me leave it like this and put a question mark if I got this right or if I screwed up by being too quick. I think this is the correct circuit, but I'll check and put it in the notes if indeed this is how it works. But you can do this, right? So some variation of this this thing here is a correct description. Yeah, final little remark, closing remark for today. So the 1 qubit case is easy, but the general case is difficult. And apart from having to handle this control qubit situation, you have to handle e to the I h, and that's an art in itself. So let me close with that. It's a thing called Hamiltonian Simulation, and it's, I guess, the jargon of the quantum computer people to say, well, handle e to the I ht as a unitary operator. Make a circuit that does this. Which is usually difficult. So if h is the sum of a bunch of terms, and these terms don't commute, which is the general situation, then this is a difficult thing because it's hard to exponentiate this kind of matrices. So this is an example where I had to work a bit to get it into my computer. Now there's, to handle this, I guess there's a standard approach, and there's all kind of, alternatives. This is like an empty statement, but what I mean is the standard way to do this is called Trotter, or Lee, Trotter, Suzuki. And that's, this beautiful identity that if in this situation, no matter what my HI are, I can use the following. So there's this identity. If I want to do this, I can say, well, let me actually do something else, which is product of I e to the minus I hi t. Now this would be exact if all h commute, right? Then this is an identity. If they don't commute in the general situation, this is not correct. But now you can do this trick, which is that you actually give this time, you make it like t over s, and then you do this whole thing s times. And by doing this trick, the commutator terms coming from h1, h2 not commuting are suppressed by a certain factor, in the sense that the mistake that you still make if you do it this way is order t squared over s. So if you make s big enough, this becomes exact. That's the famous Trotter formula for exponentiating matrices. And clearly in quantum circuits you can do this, right? You can make a circuit that does this, because this is like multiplicative, and these HIs are elementary things that you can put on the lines. And then you repeat it s times, and you approximate e to the I ht. And again, that you could do inside the box here, so to say, and then make this thing happen, and then there will be the implementation. This is often your best choice, not always. So there's a whole, I guess a whole field of investigation to see how you best do this, and there's other ways. And I already mentioned this thing called qubitization. So if you want fancy words, you can do qubitization in combination with quantum signal processing. That's another term. And that's a method. I'm only giving you the words, not the way you do it. That achieves the same thing of getting these unitaries on the table. So I'm not going to say more. In my references, I actually put a quite recent paper of the Childs group, where they review, all these methods. Trotter lead Suzuki, this thing here, a few others, and they compare, merits of one versus the other, etc. So if you want to know more, you should look up that paper. So the upshot is it can all be done, but of course, if your H is a big system where there's an actual advantage to be hoped for or expected versus classical methods, you have to handle all things in big sizes, and you need a quantum computer that can handle that. Lots of gates without making too many mistakes, and then etc. But the method is waiting to be applied. So I think for today that was my plan. It's about time to close, but maybe questions?
Are there questions? Just speak or write on the chat. May I ask a question?
Sure.
So your simulator, at a certain point, should become slower than the actual computer, quantum computer, right? Because you run a quantum computer simulator on that laptop.
Yep.
At a certain point, the laptop will take more time than the real thing.
Yeah, or it will run out of memory.
It is already like this, yes. So
yeah,
where is the catch? The catch
yes,
is that...
so if I had this n bit equals 6 and n bit equals 3, and I played with that, if I put n bit equals 40 and I say run, I'm sure nothing will happen, because this thing will run out of memory. So I think my laptop literally makes available 2 to the n bit memory slots and puts the whole thing there, which you can do with n goes to 25, 30, 35.
Okay, so the multiplication of unitary matrices in your Mac is going to stack when the size of the unitary when the space of unitaries is 20, 30, 20.
Yeah, I think so. Yeah. For sure. Yeah. You can try to go to a supercomputer that can handle a few more qubits, but I think that the best emulator platforms now handle sort of like 42 qubits or so. But that's where it stops, right?
So I never thought that multiplying unitary masses was so complicated, but okay.
You
but
can
in
see
fact, it is u to the 2n, so it's not u to the n. Is it?
Yeah, it's all exponential growth, right?
U of 2 to the n.
Every extra
operation in this group.
Every extra qubit, it doubles the dimension, so it
so it
explodes.
So there are multiplication inside the u to the 2n. 2 to the n, sorry. Yeah. Okay. So, questions?
How could you get the Greek function? Because since that you can get the energy, but you also see that you can get a Greek function. We're doing measurement, but
yes, the measurement over here collapses the system, you know, on essentially one eigenvalue, one eigenvector. And the eigenvalue I read out, and the eigenvector sits here. Yeah. Okay, so one more session tomorrow, which will be for the VQE approach.
Okay, so thank you very much for the nice lecture, and see you tomorrow, okay? Bye-bye.